All right, good morning, you guys. I just want to go over some part 2.2, and we're talking about intramolecular forces. So I know it sounds silly, but you got to go back to your prefixes. And intra is within a molecule, and inter is between molecules. So like think of it like I-75 is an interstate because I-75 goes from Michigan all the way to Florida, and it's connecting states, it's in between states. If we wanted to do intramolecular forces, it'd be more like Highway 11. Even though 11 does continue on into Georgia, for example, it's called a different highway at that point. So anyway, we're also looking at potential energy. And potential energy is going to be looked at quite a lot because remember that's kind of like the stored energy. And so you look again, and I put the text pages associated with this information so you can always go look and remember the captions and the pictures and diagrams are amazing there. So first off, with the strength of ionic bonds are super duper strong. So it does require quite a lot of energy to melt or to vaporize these solids. Basically, any way to go from a change in state, from a solid liquid gas, from a solid to liquid, a solid to gas, so forth. So it's very endothermic. Now I realize down here at the bottom you're not familiar yet with this delta H, and we will be when we get to thermochemistry, but delta H is called your enthalpy. And this is like referred to as your lattice enthalpy. And what I want you to see though at this point is that here it's a positive charge, and so it's very endothermic. So that means that energy is being absorbed more so than being released in this type of bond. Now, there are factors affecting melting points of ionic solids, and of course we go back to Coulomb's law. And remember, Coulomb's law is basically the charge over distance, so that K is simply the K constant. So we really don't have to calculate it again, we just look at the relationship between the charge and the distance. And so we're looking at, in this case, the charge of a single ion. So, for example, we can look at the charge like as in a +1 charge or a +2 charge compared to the distance between the ionic centers. So basically the distance of the ionic radius. Now, the melting point of ionic solids, obviously since ionic solids are very endothermic and they do have what we call a high lattice energy, so it's hard to break, then it's going to be harder to melt. So which compound from each set has the greatest melting point? So we're going to look at this in the form of Coulomb's law. And in the form of Coulomb's law, we want to look at what's the charge look like compared to the distance. So, for example, if you look at number 1, you have lithium and fluoride versus lithium and iodine. Now, lithium and fluoride and iodine are both halogens, but fluorine is very much smaller, so the distance is much smaller than the distance with iodine. So that's how you tell the difference. If you look down there at number 2, you've got magnesiums. Magnesium is a 2+ charge, and oxygen and chlorine again are different energy levels on the periodic table. So again, we look at the distance. When you look at number 3, you kind of have like a trifold or a bifold there because both of them are different. So your cations are different and your anions are different in this case. So now we need to look at the charges, and sodium has a +1 charge and magnesium has a +2 charge, but also the distance here, fluorine and iodine, is greatly different. So we want to look at this in this way. So take a look at the answers here. So of course, fluorine minus is smaller than iodine. So lithium fluoride is going to be harder to melt. Think of it that way. Like lithium fluoride, it's going to have a closer bond. It's going to be harder to melt. If you look at the second one, magnesium chloride is less than magnesium oxygen because, again, the energy levels, oxygen is the distance. So the distance is smaller between the bonds of magnesium and oxygen versus the bonds of magnesium and chloride. And finally, on the last one, sodium fluoride has less of a melting point than magnesium iodide because greater charges are always more significant than smaller distances. So when your distances are similar, like they're both halogens, remember the greater charges, they actually do trump the distance. So in this case, magnesium iodide does have a greater melting point, even though the bond length may be a little bit larger. Okay, so remember though, with the charges, they're losing 2 electrons. So if they're losing 2 electrons, they're actually going to be formed and connected twice, whereas a charge, if it only loses 1 electron, it's only connected once. So keep that in mind. Second, if we look at pictures, sometimes we look at these particulate diagrams and we say, which of the following metal fluorides, so we realize fluoride is common in both of them, so it must be the red, must be indicating fluorine. And again, if we would look at the ionic radius, we would realize that fluorine is smaller as an ionic radius than the cation that it's with. So which would have the highest melting point and why? Well, first off, if they're both fluorines, then you want to look at, in particular, the distance between the nuclei of fluorine to the electrons of the cation and so forth. So therefore, B would have the higher melting point. The ionic charges are +1 for both compounds, but the metal cation in B has a smaller radius. Okay. So there's something called bond energy that we're going to look at and use through what we call potential energy diagrams. And this is what I like to think about. So if you have a bond that's greater distance. So if there's an attraction from a greater distance, there's more space to get in trouble. So think of it this way. Say you've got a little kid that you're babysitting for, and the little kid is in the next room while you're fixing like supper or something like that. Well, because that little kid has more space from you, there's a higher potential of that little kid doing something naughty, right? And maybe you were the little kid. But think about when the bonds are closer, there's a lower potential energy for those electrons to do something naughty. So therefore, the lower potential energy, the nuclei is going to be closer. So the bond energy is the energy that's released during the formation of a bond. Now that sounds wild, but you think about energy is released when when a bond actually comes together. And you'll find this little saying, and we'll start to use this little saying, but when we think of energy, we think of takes to break and freeze to form. And please remember this because it will help you in so many ways. And we're talking about energy here when we say this, takes to break and freeze to form. So that means when we break a bond, the energy is taken in. When what a bond is formed, energy is freed or released. So if you can remember that, takes to break, freeze to form, that's going to help you so many times and not get mixed up. Okay, so potential energy decreases because the atoms are moving closer together. And remember, when the atoms move closer together, the potential to get in trouble, or the potential of that electron to be lost, is smaller. The same amount of energy must be added then in order to break that specific bond. So say, for example, there's 500 kilojoules that's released to form a bond, then it's going to take 500 kilojoules to break that bond. Okay, so if you're arm wrestling, for example, all right, and if you're with arm wrestling with someone of equal strength, then it's going to take the same amount of energy to win as the same amount of energy to lose. So you're probably going to be just in limbo for a really long time. Potential energy increases as the atoms move away from each other. So remember, as those electrons get more space from the other nucleus, there's more space to be lost, more places to get in trouble. The bond energy is the amount of energy that's required to break the bond between two specific atoms. And it's equal to the amount of energy that's released. So again, please remember, takes to break, freeze to form. You are going to be so glad you remembered that. And this lady named Dina Leggett, who is a chemistry teacher that you will see on some of the AP Daily videos, she is all about this. And so she's the one that taught us this, and I love it. So again, here's just another pictorial of that. And you see the enthalpy, again, the delta H or the triangle H. Don't get wigged out by that. We will learn that. But all that's telling you right now is that the energy. So you're more concerned with right now is that plus 432 kilojoules versus the minus 432 kilojoules. Because that's endothermic if it's plus, and it's exothermic if it's minus. Endothermic means energy is required. Exothermic is energy is released. So then we have something called this bond energy graph. And so you're going to have to read these a lot. And so I want you to see this like little sweet spot on here. There's something here called, it's kind of like this valley right here is the little sweet spot. And so what that is that's the perfect length, the perfect bond length for hydrogens and hydrogens. And so if the bond becomes too close, then they won't actually bond. It'll be more of like an overlap. It won't, the nuclei cannot be that close together because the nuclei are both positive and they're going to repel. And if the electrons from the atoms are too far away, if the bond is too long, then the electrons are not going to be attracted enough to the other protons, so that's not going to work. So for every, like especially diatomic, but for every bond, there's a sweet spot. And so usually we have to read these bond energy graphs using diatomics. So the one thing you have to look for is the internuclear distance goes along the bottom. And that's basically just how far it is from one nuclei to another. And that distance is in nanometers. So that's like, I mean, 1/trillionth, I think, of a meter. But this is the harder part, is the energy, and that's kilojoules per mole. And you think about, you're like, whoa, but I have energy of 0 here, and I've got negative energy here. But remember that negative energy takes to break, and freeze to form. So this is the amount of energy that's being freed when this bond forms. So that's why we're going in a valley. That's why it's a dip on this potential energy graph. That's why our energy is negative. Because again, remember, potential energy, when the energy is negative, that means it's being released. And so freeze to form, a bond is being formed. Up here, you have a less negative up here. So you have a less negative here. It's not going to form because there's not enough energy being like freed. Up here too, again, there's not enough energy being freed. I'm going to, you see this video link up here, and I'll attach this link to this reading bond energy graphs in our Schoology as well. Okay, finally the bond energy with bond length. So it correlates again with bond length, and we relate that back to the potential energy diagrams. And I'll just let you take a minute, just pause and just kind of read over this because it's very similar to what I just said, and I'm going to explain on the next slide. So as the atomic radii of the bonding atoms increase, the bond length increases. Okay, so when the length increases, so we're thinking back to single, double, and triple bonds. And so we've talked about this before, and the bond energy decreases. So again, think about if the atomic radii gets bigger, then the length between the nuclei is going to get bigger. And then the amount of energy that it takes to the bond energy that's holding them together is going to decrease. Okay, so again, this is relating to the bond energy diagrams. So let's look at it in a different form. This is where we talked about this, and I realize some of you guys too, like it's been a hot minute since you've taken it. So let's take a look. We have our bond between carbon and chlorine, carbon and bromine, and carbon and iodine. So we're going down the periodic table in size. Okay, so distance between carbon and its partner is getting bigger. So they're each a single bond. The bond energy is getting lesser because remember, the bond energy to actually like form that bond, so it takes to break, freeze to form. So the bond energy to like get that bond broken, it's going to be more to break carbon and chlorine than it will be to break carbon and iodine because the bond length is much greater. So look at the bond length here. You have 0.213 nanometers compared to 0.177 nanometers. And you might not think that's too much, but in nanometers, it's a lot. It's really a lot. So look at the bottom there, as atomic radii increases, so as the nuclei get further apart from each other, bond length increases, so the electron's attraction to the nuclei of the other is getting further and further apart. Potential energy increases because they're getting further apart. There's more room to be silly, there's more room to get in trouble, and bond energy decreases. So that amount of bond energy that's holding the bond together, it's going to decrease. So this is another model you might have to take a look at, and these are called space filling models. And these space filling models, they again, it's just like just showing it in different terms. And so we have which molecule has the least amount of potential energy associated with its bond, and which bond has the lowest bond energy. So you're thinking about again like size, because we know in this case size does matter. And so lowest potential energy you're going to have with the shortest bond length because there's less space to get into trouble. But the lowest bond energy has the longest bond length because that energy is just like there's just not as much energy holding that bond together. So again, that's a bond energy there. Okay, so bond energy, bond length, here's just the relationship. As the number of bonds, again, between two atoms increase, the bond length decreases. So you can kind of see what the electrons are sort of doing in the middle between a single, double, and triple bond. And you can also see as there's a triple bond, the bond length is much different. And so I always tell you guys, like when I teach single, double, and triple bonds, single bond is like, hey, you're dating. You've got like, a significant other, but at any given minute, it's relatively easy to break. Okay. A double bond may be more like engaged, where like, hey, you got a much closer relationship. You haven't said I do yet, so it's still a little bit easier to break off. And a triple bond is like marriage. You have a triple bond, you have much more into the relationship, the bond is much, much closer, and it's difficult to break off. Okay? So again, I like to think of it as dating, engaged, and marriage. Okay, and this is just a little synopsis too you can take a look at. And the molecules, notice, are diatomic, but those diatomic molecules go from a single, double, and triple bond. And we will find that fluorine always just single bonds, oxygen when it's together as like a diatomic, you're always going to have a double, and nitrogen, you're always going to have a triple. And finally, we have something called bond order, and bond order is the number of bonds between two atoms, and there's a little more to bond order than that, but the good thing is in AP chemistry, bond order is typically a single, double, and triple at this point. It's possible to have like a bond order of 1.5, 2.5, 0.5, and so forth. And I'll touch on that a little bit, but it's not a major thing for AP chemistry in particular. So again, just remember when the bond order increases, so as you go from single to double to triple, the bond length decreases, so it gets closer. The potential energy with the bond decreases because there's less room to get in trouble. And then the bond energy increases. It's a greater energy holding those two things together. Okay, and then here's just another look at it, a ball and stick model. Look at all these crazy models. And again, which one has the lowest potential energy? And again, the lowest potential energy, well, you have a double bond holding those carbons together. See those two curved lines on the right? And a triple bond holding the carbons together on the left. You see the two curved lines and the straight line holding the carbon together. So again, you're thinking you got the lowest potential energy because a triple bond's the shortest bond length, and you have the highest between the two, the highest potential energy, but the lowest bond energy because of the longer bond length. So think about, we've got some energies here going on. We've got potential energy, we've got bond energy, and so we need to kind of like clarify. We've even hit on some lattice energy at the beginning. So we're going to start making a poster with all of our different kinds of energies so we don't get them intermixed up. Okay, finally, just the models. I want you guys to kind of understand the difference between the models that we've seen throughout this. All right, so you guys have a wonderful day, and I shall see you soon. Take care.